Thank you. So today it's our honor to invite the Dr. Sudhir Mercy to give us a talk about the aerobic granules and its commercialization. Actually, this is a part of the activity conducted under the aerobic granulation work group with the EBNet. Dr. Sudhir Mercy is the Chief Executive Officer of the New Hub Corp. He is also adjunctive senior research scientist at Columbia University and senior vice president of the International Water Association. Sudhir was the innovations chief for DC Water until 2018 and led the development and implementation of the authority's innovation strategy. Sudhir led the concept development for over $1 billion in new engineering and construction in the context of the circular economy. Sudhir has an MS in environmental engineering and a PhD in civil engineering from the Virginia Tech. He is a professional engineer and a licensed treatment plant operator in the USA. So before I head over to the Dr. Sudhir, probably I just take 1 minute to give a very brief introduction about the history of the aerobic granules. Actually, compared with anaerobic granule developed relatively late. It was in 1991, 1992. There was the first paper published on the aerobic granules. That is a continuous flow reactor. Actually, that reactor is the traditional UASB with a high reactor height to diameter, and the aerobic granules can be formed, but granules very easily to turn into the fluffy granule and or disintegrate into the pieces. So granules, in one word, granules were not stable. So that's the reason that two papers didn't cause much attention. And until 1997, the first paper about the aerobic granule in sequential batch reactor was published by Professor Mark Lustrecht from the University of Delft. And from the 1998 to 1999, Professor Teju Hua from the Nanyang Technological University started fundamental research on aerobic granules. And since on, I think that the aerobic granule research is a hot topic. And in 2005, Royal Haskell DHV built its first industrial prototype, which is called the Narendra process. And after that, aerobic granule technology, mainly Narendra process, was commercialized and adopted by many countries. Here in the UK, actually the UK has constructed and operated 13 aerobic granule-based sewage treatment plants. And one of them is the largest Europe aerobic granule sludge sewage works. It deals with more than 320,000 population equivalent, and with an investment of more than 100 million pounds. And as far as I know, that all of the UK's Narendra process is operated in sequential batch mode. In USA, actually the USA look at the aerobic granule technology from the both sequential batch operating mode and continuous operating mode. That's the reason today we invited Dr. Sudhir Mercy to give us the talk about the aerobic granulation in continuous operating mode and its commercialization in USA. Probably we also want to look at if there's any possibility or if there's a prospects that continuous operated aerobic granule technology can be adopted in the UK. So now I head over to Dr. Sudhir Mercy.
Hello, can you hear me?
Yes, yeah.
Okay, thank you. Thanks for this introduction, and I think you summarized the history of aerobic granulation quite well, including the full-scale implementations. The concept of indents, which is really, if you look at the approach that we have taken for densification or aerobic granulation is really there's so much infrastructure that's already been built in the United States. For 16 years, I worked at one of the world's largest advanced wastewater treatment plant, the Blue Plains plant, and it's impossible to implement a process, a new process in a lot of these plants where the hydraulic profile has already been defined, and from a civil engineering perspective, building tanks that are reasonably uh, uh, maybe 15 to 20 feet deep in uh, in the ground makes sense from a perspective of geotechnical as well as civil engineering and structural engineering approaches. So given the hydraulics of how we typically do things, and given the structural approaches and geotech approaches of how we do things, especially in the United States and Europe, where most of the plants have already been built, how do we bring to such plants the concept of aerobic granulation or sludge densification? And so the approach we took, this was at DC Water and HRSD. Uh, uh, this is Charles Bott at HRSD, who is the head of innovations there. And this is myself a long, long time ago, where I was the head of innovation at DC Water, two public utilities, by the way. We sought the approach of maybe using hydrocyclones as a separation approach for aerobic granulation, and I'll explain the whole concept. The other two-person that are important here are Bernard Vett. Bernard is one of the inventors. He's actually located in Innsbruck, Austria, and the commercials in Europe are being led by him through Innsbruck, Austria, and then the commercials in the United States and North America is led by me, and then we also work in the rest of the world through licensed distributors. The distributor in the United Kingdom is Sweco. Henk Wim de Moy, so many of you may know, is leading up that effort in the United Kingdom. I'll and rather than sell a process, we wanted to go asymmetric, especially for plants that have already been built. We didn't want to sell a process. We wanted to sell actually equipment, a supply, and so our approach is not to sell a process like Narita, but on the other hand, to sell a supply, which can end up being very economical for plants that are at capacity and need to expand. And so what we are doing is developing an approach for physical classification and not selling a process per se for aerobic granulation. The consultants and the utilities do need to look at how to actually make that plant a little bit more plug flow to afford that aerobic granulation process. And I'll describe some of all of that in my presentation. So what is gravimetric selection using hydrocyclone? What we try to do using such an approach is the underflow of a hydrocyclone will have the heavy material coming out. The overflow have the lighter material coming out, and this is the feed. And so if we can get the heavy material in the underflow and the lighter material in the overflow, then we can possibly retain that heavy material, and that heavy material is then dense and then supports an improved SVI. The lighter material, which hopefully contains filaments and flocks that we don't want, can then be wasted. And over time, the entire system ends up with heavier material. It's really simple. One would wonder why no one ever did this maybe 20 years earlier. It's basic physical classification. In a typical hydrocyclone that we supply, we can have a body extender. We can change the vortex finder, or we can change the spigot at the bottom. And by changing any of those three, we can actually make some decent amount of modifications to the hydrocyclone. This is an example of what one might see at any plant which implements a physical classifier like a hydrocyclone. On the left is a feed, SVI, the settlement of the solids from the feed. The middle is the settlement of the solids from the underflow, and to the right is the settlement of the solids in the overflow. And you can see, and these are all at the same concentration. Okay, so the very same concentration, and you can see the underflow settles much faster than the overflow, and we try to waste. In fact, we waste the overflow and relative to the feed and the underflow. And in 30 minutes you can see the difference as well, but you can also see the difference in 5 minutes. And so selective sludge wasting, which is what it is by physical classification, can promote aerobic granulation really in almost any existing plant configuration. There are tens of thousands of CAS, continuous flow activated sludge facilities already built worldwide. There are IFAS systems that are already built worldwide, sequencing batch reactors, membrane bioreactors. So there's this already that existing infrastructure. So how do we actually use something like this, which is a hydrocyclone with skid, to improve capacity by between 20 and 30%? Typically, it's around 30% increase in capacity of a plant. There are nearly 80 implementations worldwide for a technology that we've launched only in the past 5 or 6 years. So where does one place the indents unit? One can put the indents unit in the waste stream. So let's assume you have a continuous flow activated sludge process with an anaerobic selector, or maybe even just simply an anoxic selector. One would eliminate the regular waste stream, take a small amount of RAS, typically 150% of what you would need to waste. The 1x will go into the waste stream, and the remaining 0.5x is returned. And that contains the dense material. But really what we are doing is out selection. We are out selecting, or we are deselecting the pore settling material. And by deselecting it, we are hopefully retaining the good settling material. This one shows the typical hydraulic and mass splits associated with our approach. You'll see that about 70% of the flow is in the overflow, and about 30% is in underflow, giving that 1.5 factor that one needs to manage into the hydrocyclone system. So if you know your waste volume, then it's very easy to design this hydrocyclone system. And you can see in this PowerPoint slide, the granules are retained in the underflow. It's very fine flocks that go out in the overflow, sometimes filaments, depending on what your objectives are, and the mixed liquor in the feed. Our approach is not to try and maximize aerobic granulation. Our approach is to try and get a flock granules, what I would call a Goldilocks approach. We don't necessarily want to operate in a fully granular approach. We don't believe that's what we should try to achieve. But we do try to achieve one, SRT uncoupling. That means the low SRT organisms might be present in the flocks in a properly designed system. the high SRT organisms in the granules. So it's very much similar to how an IFAS is operated, where the higher SRT organisms are on plastic media. Here, the higher SRT organisms are in the granules. The low SRT organisms are in the flocks. So it's this combination of flock granule approach. What we want to do is improve the mixed liquor solids. So we want higher MLSS inventory in the process. So that's an objective. And one can do that by improving the settleability of the process, but we also want more active mixed liquor suspended solids. And by doing this SRT uncoupling, we would have the ability to manage the active fractions associated with what we want to support in our process. Our belief is that granular only systems have too long an SRT and they carry debris. They carry a lot of organic and inorganic debris, and that's not our intent. They also may have too much diffusion resistance. Uh, some of our systems now are operating in what we call it SND mode, with very little air added. So we don't want too much diffusion resistance for aerobic organisms. On the other hand, flocculant only systems have much lower inventory that they can support in the process, and maybe not enough diffusion resistance for anaerobic organisms. So we want this Goldilocks approach, and our operating zone is somewhere around here in the flock granule approach. Typically, we could have somewhere in the order of 2 parts granule to 1 part flock in our indent systems. And our SRT uncoupling could be one. So the SRT of the flocks could be in the ballpark of, say, 5 days, and the SRT of the granules could be in the ballpark of 25 days. So that's the uncoupling that one could envision. The this is a an SVI test where we have 1,000 mils of mixed liquor being subject to settling, and the feed is in the blue, the overflow is in the red, and the underflow is in the green, and you can see the difference. Can you see my slides? Okay. So what I'd like to show you here is the flock density. This is a test that we did using Percol, and what we typically see is that the overflow has a flock density somewhere much lower than, in fact, 1.03. It's somewhere in the range of 1.01 to 1.02. And the underflow has much heavier particles in the order flock density of higher than 1.03, but could be much higher than that. This is the sludge volume index at one of the plants in Soyen. This is somewhere close to Munich in Germany, where the blue is the feed, the red is the underflow, and the green is the overflow. And over time, many folks ask, if I'm wasting bad settling sludge, will my dewatering be impacted? But in reality, what happens, that's just a transitionary period. Over time, the overflow SVI actually is better than sometimes the feed SVI. So over time, the SVI gets better for all the 3 fractions: the feed, the underflow, and the overflow. And so while the feed SVI could get down to the 60 milliliters per gram, the overflow SVI is also not too bad in the 150 milliliters per gram or so. We've implemented indents in A2O configuration, and so this is an example of an A2O type configuration in Denver, where we have an anaerobic zone, anoxic zone. So anaerobic zone in the first 2, the anoxic zones, and then the aerobic zone in the rest of the process. And these are the hydrocyclone skids in Denver. There are 8 of these hydrocyclones in that skid for this strain. And at this plant, what we see is, for example, there's a control train, which is the full-scale AB4 SVI, which is in red, could be as high as 160 milliliters or 180 milliliters per gram. And then as we start the indents, you can see that the SVI starts dropping, and you can get down to anywhere between 60 and 80, sometimes 100 milliliters per gram, depending on what your starting SPI was. What you also see, which is I think important to note, is an improvement in the clarifier blanket levels. So the clarifier blankets go from, in this case, as high as 3.5 feet to below 2 feet. And in almost every plant we've operated in dense, we see our clarifier solids concentrations, our thickening function improves, and so our clarifier solids concentration increase. At our plant, at a plant in Strasse in Austria, the solids concentration in the underflow is as high as 1.5 to close to 2%. And so what that does is you recycle less water. So you can reduce your RAS. So typically our RAS can go down to between 25 and 30% of Q. And so by reducing your RAS flow, you actually increase your driving force. You increase your hydraulic capacity of your process because now you're sending less RAS flow, and so your forward flow can compensate for that, as well as our driving force. It's less dilute, and so the driving force of our substrate to get into the granules improves. So not only do we improve the SVI, we improve our thickening, and those are actually complementary and creates that virtuous cycle. This is an example of another A2 plant in Dijon in France, where they had a control line and a densified line. And in this plant, you can see the hydrocyclones out here in the top right portion of the figure. It's an oxidation ditch plant with an anaerobic selector. And at this plant, the control line is in blue, and the indents line, the densified line, is in green. And this is 2 years worth of data. And you can see that in the first year, we see this gradual improvement. And then in second year, it actually continues to improve with an SVI eventually less than 50 milliliters per gram. And while the control line has this typical seasonal pattern of poor winter sludge settleability and much more improved summer sludge settleability. We've implemented indents in the combination of using chemicals such as aluminum. We have a plant in Ephrata, Pennsylvania, where we actually add chemicals and do BioP simultaneously in the process to get low SVIs. So we don't have too many of those applications, but we've even implemented indents in under conditions where the phosphorus limits are quite stringent, and to try and manage both BioP and ChemP in the same plant. We've also just started implementing indents in non-BioP systems. This is an example of a plant where they have a classic MLE type approach. This is the Urbana plant at HRSD. It's a very small 0.1 mgd plant where we first tried indents with an MLE approach, modified Lutzack-Ettinger approach. Some people may call it just an anoxic process with a internal mixed liquor recycle. And we had a control train and an indent train at this plant. This is the small plant with the hydrocyclone skid there. And you can see that in the indents mixed liquor in the effluent of the aeration mixed liquor, In the control train, the settling velocities are in the ballpark of between as high as 1 to as low as zero point 0.2 meters per hour, and the hydrocyclone train maintains fairly reasonable settling velocities in about 1.5 meters per hour. This is another larger project for an MLE plant, and here there's an anoxic selector. The anoxic selector is 15 minutes. It's a project implemented by Jacobs at the Upper Occoquan Sewerage Authority, and this is a combined plant. So this is say 1 year worth of data of the combined plant. Then there's almost 1 year worth of data of a split plant, and then with the implementation of the hydrocyclones. And you can see that there's an improvement in SVI associated with that plant relative to the control train. At this plant, they used a particle size analyzer using laser diffraction to understand what was the particle size separation between the control and the indent strain and the the overflow and the underflow. The west is the control train and the particle size distribution of that train, and then the east is the indent strain, and you can see that the particle size moves to the right. With typical particles in this MLE plant, it's a non-BioP plant, in the range of 250 microns average particle size. And you can see the underflow particle size has got this double hump, suggesting some amount of SRT uncoupling, but then the overflow SVI is in the yellow line. For the same plant, they've done many flux analysis under summer and winter conditions, and you can see that in the summer there's not that much of an improvement in flux between the control and the indents line, because the control was settling quite well in the summer. But in the winter, where the sludge bulking did occur, that's when the indents line actually improves relative to the control line, and the two, the winter and the summer conditions are much similar for the indents line and quite different for the control line. And so the indents line does not necessarily improve settleability if the settleability is already doing quite well. This is an AO plant. This is an anaerobic followed by an aerobic plant. Not so the aerobic approach was operated in an SND mode, simultaneous night-D-night mode. This was a Brown and Caldwell project in Pueblo, Colorado, where there's an anaerobic zone, but this aerobic zone is operated in an SND mode, and with AVN as a controller. And this is the full-scale plant, and the SVI before the implementation, and then after the implementation is considerably improved. And Brown and Caldwell is, I believe, calling this their approach of intensifying treatment using SND, AVN, and hydrocyclones. It really simplifies the process flow configuration of the plant. We've also implemented indents in an IFAS train. This is the James River plant at Hampton Road Sanitation District, where indents is implemented in an IFAS plant, where we have an anaerobic selector followed by an IFAS zone in an A2O configuration. We've implemented indents in an SBR, a modified SBR approach. This is a plant configuration in Soyan. There's a modified SBR called a BioCos system, where there's an aeration tank followed by 2 clarifiers, and there's an anaerobic zone that is typically added around here. This is the soyan plant, and you can see this is before the setup. The idle is when the when a permanent installation of indents was being implemented, and this is the SVI going up to 160 in the winter, going back down, and then with the indents, the SVI is much more stable over several years. We've implemented at one location in China, at a biogas plant there as well. And then finally, step feed. In fact, I saved the best for the last. Step feed is actually our favorite configuration of implementation of indents because it doesn't have the IMLR, it doesn't have the mixed liquor recycle. Step feed by itself does some flow intensification, and so combining the flow intensification of step feed with indents is very synergistic because because it's less plug flow. Sorry, it's more plug flow than a typical MLE type configuration. And this is an example of a plant where we converted an MLE configuration where nitrate is recycled into a two-pass step feed configuration to get pretty much the same output in terms of TN and TP, but using step feed, where we converted 10% into an anaerobic zone, and the remaining 40 each, and then 40% into a alternating aeration, intermittent aeration, anoxic aerobic combined zone. And this is an example of that plant in Alta Badia in Italy, where we are now 7 grams per liter, between 6 and 7 grams per liter of TSS in our indent strain. And this plant has a AAA settler that precedes the indent strain. And so really the intensification has been huge at this plant because we not only do carbon redirection using the AAA settler, but we also have the indents doing the intensification in the biological step. And so the combination of AAA indents can do intensification, but also help create energy neutral plants because we send the carbon to anaerobic digestion. Indents with MBR. Um, we have licensed the use of indents with MBR to the ZWeed membrane, which is now owned by Veolia WTS, and this is a example of before hydrocyclone, the cleaning cycle of membranes versus after hydrocyclone use, and the transmembrane pressure before and after implementation of the hydrocyclone. And again, the concept is the same. If we can out-select and get rid of the fines that will typically foul the membrane, then we can have, perhaps, we don't know yet, longer membrane life, less fouling, but even perhaps an increased flux rate. We don't know all of that yet, but we certainly have seen improvement in or reduction in fouling. That's pretty much it. It's a very simple approach. What you need is a cyclone mount with pressure transmitters and flow meters. We strongly recommend AVN control because that helps with making the process more plug flow. And one last thing, anaerobic zone modifications such as just adding a simple baffle wall and improving hydrolysis, inline hydrolysis in your anaerobic zone becomes important, especially in the winter, to release the RBCOD. That will then be important to create the large granules, to get the driving force to produce granules. So the mods for CAS configuration is not that substantial, and could be easily retrofitted in almost any plant. And with that, I'll open the floor for questions.
Thank you very much for your interesting talk. I think that is this intensification is quite different from the Narenda based process because you don't just want to form the granule, you just want to improve the settling ability and take advantage of the both flocks and granules. So
I would say, yeah, the opposite. We want to actually get the best of both worlds, and we're transparent, right? Our approach is fully transparent. It's not a black box, and I think it can be implemented in almost any configuration. It's not tied to a phosphorus removal configuration.
okay, so we have a question from the chat. It looks like it takes time to change the underlying biology. Do you speed that up by using lots of the hydrocyclone to start with before taking over with a few number later?
Yeah, you're right. A minimum of 3 SRTs are needed. We would prefer to start in the summer or spring. Springtime is a good time to actually start this concept because you can drop the SRT in the summer and get ready for the winter. So by timing the approach of when we install the hydrocyclones and get it started, we can speed up the implementation, especially if we can drop the SRT by half in the summer to start wasting out the bad settling sludge and start retaining the granular material.
Okay, I think there's another question from the Sonia Heaven, Professor Sonia Heaven. Absolutely fantastic. As you say, why hasn't this been done everywhere? In your last example, you mentioned reduction in membrane folding. Very interesting. Can you tell us a little more? Appreciate not much evidence yet.
Yeah, we don't know too much yet. There are 2 large pilots, demonstrations that the Veolia WTS folks are starting this in the next few months. So we are really looking forward to understanding that better. But what I showed you was a part of a publication that was published associated with some of the work done in Singapore.
Okay. I think there's quite a few publications about how the aerobic granular sludge can reduce the membrane folding. But what I see is from the lab scale study, not from the pilot or the full scale. I think we have another question from the Jacob Mesos. How it affects aeration and how do we carry out the process design? For example, what becomes the key design parameter, as it is a bit difficult to calculate SRT granules?
Yeah, so that's a good question. The key design parameter for now has been the improvement in SVI, the projected improvement in SVI. But where we are headed is a full-fledged model in Sumo, and I think Jacobs uses Sumo as well, but where we are implementing this SRT and coupling approach. So at a minimum, from a design perspective, you can take credit for improvement in SVI and therefore the capacity associated with it. But obviously, we are not taking full credit associated with all that could be realized with indents, and that's quite a bit of work in progress in developing the models to support such an effort. And I think there are folks in Jacobs that are involved in some of all of this as well. So I think if this individual from Jacobs could connect with me, I can then help out in some way.
Okay, thank you. So another question is about the cost. So it seems because if we have if we need to retrofit the existing sewage plant, if we just add additional cyclo or dense equipment, it seems quite simple. But how about the cost? How much additional cost that we need to put into the sewage works for upgrading? If we target the same level of the performance.
Yeah.
Quality.
Yeah. So I would hazard and say that if one were compared to an upgrade, let's say the projected improvement is between 20 and 30% of increase in capacity. And I say that with some sort of conservatism. The plant in Denver, in Colorado, the utility themselves in their capacity report projected a much higher increase in capacity from their trials, between 50 and 75% increase in capacity. So I'm actually being conservative, but with that increase in capacity, say 20 to 30%, the cost of the hydrocyclone is a fraction, maybe 10 to 20% of maybe 10% of that cost of putting in new concrete tanks. So it's favoring a mechanical improvement over a hydraulic or adding more tanks and all of that goes into adding more tanks. The other thing that is of interest, which is quite curious, is often when a plant has poor SVI, the immediate response of sometimes of a plant having poor SVI is to add new clarifiers. And so there's this direction of, hey, I'm going to add clarifiers because I need to manage my capacity, and you go into a vicious spiral because you add more clarifiers and then you retain more bad settling sludge and you create even worse SVI. And so you start with a bad SVI, you create worse SVI by adding more clarification capacity because you're not addressing the root cause of the bad SVI, which is keeping the bad settling sludge in and not out selecting it. And so often we add infrastructure, and certainly I've participated in some of all of that. Is we add infrastructure to address poor settleability instead of actually addressing that root cause. And so to answer that question could be complicated because if you're starting to add clarification capacity to a plant, I would almost propose first start looking at maybe improving your SVI before adding clarification capacity. And you could do that by out selecting some of these bad settling sludge.
Okay, thank you. So there's a question from myself. I'm very interested in the nitrogen and phosphorus removal. So by the intensification, you said the 2 parts in granule, 1 part in flux. So I noticed that your mean size is around the 250 micrometer. So I guess for the granule, probably the granule's size could 300 or 400 micro.
So in that range, 250 to 400, yeah.
Yeah. So in this case, did you observe for example, if we don't talk about the increase of the capacity, if we just compared with the previous pure activated sludge system, did you observe the improved nitrogen removal? Did you observe the simultaneous nitrification, denitrification conducted probably by the granular sludge because of the dissolved oxygen resistance in granule?
Yeah, certainly. I think at least some of the implementations that are headed is in that approach of trying to achieve SND. We've seen two approaches of actually doing this. One is at a plant where the entire aerobic zone was converted into what we'd call it an SND zone, low DO of between 0.3 and 0.5 milligram per liter. but more close to 0.3. And then another plant where only the last part of the plant was converted, so tapered aeration into an SND zone. And what we were surprised is the denite capacity in that post aerobic zone. And we are still scratching our heads a little bit about it. But what we believe is happening is that the hydrocyclones tend to accumulate more of the denitrifying polyphosphate accumulating organism, DPAOs. And these DPAO organisms are good at storage, but also good at denitrification. And their SRT requirements are somewhat higher because if you take into account the small amount of anoxic capacity that is typically present in most plants, it's not enough to actually keep these organisms going. But with SRT and coupling with indents, now we have these phosphorus removing organisms, perhaps in the granules, storing the carbon and allowing for that carbon to be used in the downstream zone. And so we are not only able to achieve good phosphorus removal, but also using that same mole of carbon, we are also able to achieve denitrification capacity in that SND mode that we talk about. But it's a lot of new stuff. We're on a journey of discovery and learning about what are the other opportunities associated with indents. Broadly speaking, if you see the work done by Andrew Schuler, where he showed that the BioP organisms tend to be denser than the non-BioP organisms, and he showed that the BioP organisms have specific gravities in the range of 1.03 or greater. We see that might be true. That the biological phosphorus removal organisms tend to be in the underflow of the hydrocyclone. At one plant, we looked at DPO activity between indents and control train, and we saw 4 times the DPO activity between the indents and control train. This was, of course, in the summertime, and so. Does it improve storage? Does it improve the use of that carbon under anoxic conditions for phosphorus removal as well as for nitrogen removal? I mean, all of that, we're just starting to see that information, but eventually we'll need to model it as the gentleman from Jacobs mentioned, and try to improve understanding.
So did you carry out the microbial community analysis to validate if there's the accumulation of the phosphorus accumulating bacteria?
Yeah, I think at this project in Pueblo, Colorado, that was done, I believe, with Belinda Sturm of KU, where they looked at not only looked at the microbial activity, but mainly they also looked at the kinetic test associated with adding nitrate as a substrate and looking at P uptake as well as denitrification.
Okay, so there's a question from the chat. I'm a student operating sequential batch reactor and try to increase the settling ability. What would be the most critical operation parameters that can increase the settling ability in your past experience? Increase. This is SBR. I think probably settling time is most critical operating factor to increase the sludge settling ability.
So yeah, it's kind of interesting. The key, I think, to improving sludge settleability is to out-select the poor settling organisms, and sometimes the fallacy is to believe that you out-select the poor settling organisms by managing settling time, which one could do, but if you can waste, because if you look at the mass of organisms, if just look at the SRT equation. SRT equation is in the numerator is the inventory X times V, and in the denominator is the mass wasted. Okay, just the SRT equation, and you're wasting mass, and most of the mass you're wasting is from the waste stream, not in the effluent stream. You know, QEXE is small relative to QW times XW, in the waste stream, the mass wasted. And if I can affect that mass wasted and get rid of the bad settling material in that mass wasted, uh, then you can get good settleability. And I think that's key in managing organisms and inventory is to get rid of the bad settling organisms in that mass wasted. And maybe I'm
Okay.
I feel, yeah.
Yes, that's a good explanation. That is about the selection. So we select the good, the well-settled sludge. So in our lab study, if we use the synthetic wastewater, we notice a phenomena. Sometimes we form the granular sludge. Granule sludge settling ability is quite good, but the after settling, the supernatant is cloudy. Sometimes, not always. So we don't know what happened. So did you observe because there's a lot of clouds in the supernatant, that's the reason it becomes cloudy. So did you observe for your intensification systems, sometimes the supernatant could be, turbidity of the supernatant is higher?
So so that's a good question. You know, there are some conditions, I believe, maybe at one plant where the plant operator said that my SVI is too good, and and uh, and so the plant operator tried to bypass the hydrocyclone train because the SVI was getting too good, and and the reason it was too good was because the turbidity was increasing in the effluent, and the operator wanted more flocculant material uh, to to uh, to be able to get the filter flock effect associated with turbidity, and they saw that improvement in in reduction in turbidity when when the SVI was too good. But you know, other than that one plant, an anecdotal observation, in general, the SVI has been good, and the turbidity has also been fairly manageable because we don't typically have all granule systems. It's a flock granule mix system.
Okay, so because the flux, when it settled, it flocculate, so probably also can remove the clouds. Yeah.
Yeah.
About because your key equipment is a cyclone. So for the cyclone, does that need the instrumentation? How to control that? It is very complicated, or it is very easy to do.
Yeah, the cyclone equipment is fairly simple. It's a 10 cubic meter per hour hydrocyclone operated at 2.1 bar, and it has a pressure transmitter and a flow meter, and that's about it. We prefer the plants to use the AVN controller because that improves the plug flow nature of the plant, because by either doing SND or alternating aeration, you don't have the Imler, you don't have the mixed liquor recycle going back to the front, and that creates more plug flow, and that improves granulation. Step feed is a good thing. AVN is a good thing. But whatever really improves plug flow characteristics is a good thing along with indents.
Okay, so for example, in the wastewater treatment plant for the operation performance, sometimes we need to adjust the aeration.
Yeah. So
sometimes we need to adjust the biomass concentration. So also for cyclone, do you need we need to adjust any parameters to get the better performance, or we can just fix the certain parameters?
Yeah, so certainly optimizing aeration is something that should be considered. Um, um, and and typically in our avian controller, and by the way, you could use an ABAC controller as well. But in the avian controller, what we typically do is we either go alternating aeration or we do an SND approach. And so in that aerobic zone, we try to build anoxic capacity in the aerobic zone, and therefore you don't need necessarily a separate anoxic zone. And by doing that, one can improve performance. In other cases, what we do is we add the step feed arrangement, which also eliminates the recycle, and that also helps with plug flow. And then the aeration in that aerobic step could again now be alternating or simultaneous to improve the capacity utilization in that aerobic step. We So that's often what's done at many plants, but there are lots of plants where we've retained the Imler. In fact, I would say more than half our plants, including this plant in Denver, we've retained the Imler, the intermediate mixed liquor recycle, but then we change our feed locations. So we manage our feed locations so that we minimize the addition of wastewater into the same zone where the Imler comes in. So if the Imler is coming up into the first anoxic zone, we want to minimize the amount of wastewater going in there, because now we are sending carbon into a zone where it's immediately being diluted, and that will create filaments. So we want to send most of our wastewater into a zone that is fairly plug flow and not subject to dilution. And so very few things really in terms of plant mods that can really improve settleability along with the selective sludge wasting. Where you add your feed is important. I would say the most important is RAS, RAS thickening, and sending less RAS flow back. And so sending maybe 20 to 30% RAS flow back instead of the typical 100% or 50 to 100%. That is huge in terms of improving densification. I mean, it's very few things, but almost everything under the plant operator's control.
Okay, thank you so much. So last minor question. So how about the sludge dewaterability of so after the eutessification, so dewaterability improved or still same?
So at Denver, I think they looked at centrifuge thickening and they saw that the thickening improved, but I don't think they saw any changes per se in the dewaterability after anaerobic digestion. But I don't. We haven't really looked at it too much in detail. What was interesting is at the same plant in Denver, and I think Belinda Sturm at KU is looking at it more. They saw improved removal of E. coli, and we don't know why in the hydrocyclone train, but that's all very curious to me yet. But certainly at least one plant they've seen improvement in thickening.
Oh, okay. Probably dewaterability that we can do the further study to see if the dewaterability can be improved. I think last trivial question from the Sonia Haver, Professor Sonia Haver. You present some excellent aerial images. How did you took that pictures? Did you take that pictures from Drew satellite?
I tell you, most of these images were from the plant operators, almost all these images. So I don't know where from the plant operators themselves.
Okay, I think it is time for us to close this webinar. Thank you so much. So if any person has any questions, can they, for example, if they want to know more about the eutessification cycle, can they contact you?
Please.
Yeah.
Yeah, absolutely.
Okay. Thank you so much. I think that's all. Thank you for every attendant.
Thank you.
Yeah. Thank you.